Okay. Hello. Hello, hello. Anybody and everybody that's out there. Wait. Okay, there we go. I was just checking my audio. I had to do, as always, the weird thing where I have to cancel the stream and then restart the stream, or else the audio goes strange. So that was why I did that. Well, anyway, yeah, so today I want to talk about double pendulums. Actually, I was trying to figure this out. I couldn't figure out whether because obviously the plural of pendulum is pendula, but then is the plural of double pendulum double pendula? Because that just sounds weird. So I kind of said double pendulums, but I avoided it by just saying the double pendulum, as if there's only one. But I don't know. Does anyone have any strong preference? Is it double pendula or double pendulum, the plural? I've no idea. Probably double pendula, but I don't know. Anyway, so as you can probably see, so I've got two screens up. I've got my usual whiteboard, where we'll talk about sort of the physics side, and we'll derive some of these equations that describe how a double pendulum works. And then on the right, I hope you can see it large enough. You might have to maximize it, but I think hopefully you can. You should be able to see my MATLAB script, where we'll be writing this code to simulate the motion of the double pendulum. Hello, Rooster. How are you doing? Hello, Theoretical Fizz as well. Good to see you. Good to see both of you. You can see it fine. Okay, awesome. Nice. So you'll also notice I've cheated a little bit in that I've already typed out some of these functions that I'm going to need to use. And that is, of course, because, I prepared for this. So, I mean, I've coded this in advance, so I know what I'm doing. I'm not coming into this totally blind. And I thought it would save me the pain of having to type out all these very long expressions, which we'll derive on the board in a minute. And it'll save you the pain of having to watch me type them out and then eventually debug them when I realize I've typed something out wrong, which absolutely would 100% happen. But that's the only cheat. Other than that, we'll do everything coded from scratch. And I'll explain what all of these different functions are that have appeared at the moment in the code as we're going through. But this is just so I don't have to retype them out again. So anyway, I guess let's talk a little bit about what a double pendulum actually is. So I suppose you can see kind of zoomed in here the idea of it, and I suppose the name is fairly explanatory too. It's like we take one pendulum here, which in this case this is on a fixed hinge, and this has got some little bob tied onto it, which I've called mass m1, and then onto that little bob I freely fix another light massless rod, which has a second bob tied onto it. So this rod along here is totally free to swing about the mass it's attached to. We assume it's, a totally frictionless, smooth hinge and so on. And we also assume that all of the mass is concentrated just in these bobs. The rods themselves have no mass. They've got lengths I've called L1 and L2, and I've described the entire configuration of this system, position configuration anyway, can be described by two numbers, and that is the angle this first rod makes to the vertical, and this second angle the second rod makes to the vertical. Okay, with these two numbers you can totally specify the position of the system. Of course, it'll have some speed, angular speed, in both of these rods, but that's something else. So this is the idea of a double pendulum. And now the technique we're going to use to get these equations of motion. Now, of course, this is all totally. How many degrees of freedom does it have? Well, it's got two position degrees of freedom, but then I suppose it's got two. You could have two independent angular speeds. So I suppose if you were trying to count, degrees of freedom in like a phase space, it's got two possible angular speeds, theta1 dot and theta2 dot, and it's got two positions, angular positions, theta1 and theta2. So in that sense, I suppose it's got 4 degrees of freedom. It's a 4-dimensional phase space to it. So the technology we're going to use, the physics technology, or the mathematical technology, we're going to use to approach this is Lagrangian mechanics. Now, we're not going to go from scratch and talk about Lagrangian mechanics. I've talked a little bit before about Hamilton's principle in an office hour a while ago. We're just going to really use this as a computational tool. I think actually another physicsy streamer, PhysicsO, who I'm sure most of you all know, has a really good series of videos on Lagrangian mechanics. So if you want to know more in detail about that, you should take a look on his YouTube channel or something. But we're just going to use it as a computational tool. Okay. So this computational tool in Lagrangian mechanics requires us to define this quantity, this scalar quantity that I've given this rather fancy calligraphic L as is standard, which is the difference between the total kinetic energy of the system, which we call T, and the total potential energy of the system that I call V. So all we have to do now is we have to write down what the total kinetic energy is and what the total potential energy is, find the difference between them, and then this mathematical technology of Lagrangian mechanics allows us to find the equations of motion of the system by just plugging them in to these equations called the Euler-Lagrange equations. And these will give us two equations of motion that describe the system. We're using angular kinetic energy. Well, we are using, so yes, we're using it. I see. There is a slight error here that I didn't correct. It's correct everywhere else. I just didn't correct it there. So we're using angular kinetic energy for the first bob, which is just, it's just going around in a circular motion with some radius L1. The only thing that will affect its kinetic energy is θ1 dot. Then the second one, this bob's motion is a little more complicated because actually this is not confined to the arc of a circle. This can go, as we'll see, because we'll produce some nice plots, it can go all over the place. It can trace out, all sorts of complicated shapes anywhere within a radius a radius L1 plus L2 of the hinge. It can trace out any sort of crazy shape you like in here, though. So the kinetic energy of the first particle of M1 is straightforward enough. That is just going to be its linear velocity squared. So it's undergoing circular motion around this, around the hinge. So its linear velocity is just the angular velocity, which is omega1 dot times by the radius of its motion, L1. Okay. But the linear velocity of the second particle, M2, is a little more complicated. So what we do here is I think about the motion first of M1, of, the hinge that M2 is tied onto. So I think about what particular velocity this hinge is moving with. I find, for example, the horizontal component of the hinge's velocity, and then I add onto that the horizontal velocity just due to the second particle rotating about the hinge. Okay, so I add up these two horizontal velocity components and I get the overall horizontal velocity of the second mass of M2. Now, you could do this differently. You could, if you like, write down a position for the second mass. So you could write down, well, its y-coordinate will be whatever this length here is. So, L1 cosine θ1. And then you have to add on this second triangle length here, which will be L2 cos θ2. And then if you like, you could differentiate that. And that would give you the total horizontal velocity of the second particle. And then you would do the same thing, except now, total vertical velocity of the second particle. And then you would do the same thing. You would find the length of this triangle, which is L1 sine θ1. Then you would find the length of this triangle, which is L2 sine θ2. And then you would differentiate that, and that would give you the overall horizontal velocity, which you would then differentiate. You would differentiate it to get the overall horizontal velocity. And then you would square and add these to get the total velocity, the net speed of the horizontal and the vertical speeds. Exactly, using the chain rule. But I've kind of skipped this step. So what I've done is I've just added the velocities right away. Because we can do that. You can think about the horizontal and the vertical velocities, oh, hello, Sly, of the hinge, and then you can think about the horizontal and the vertical velocity of the mass with respect to the hinge, and then add these up. Okay, so in doing that, I find here, in this first bracket, I'm finding the horizontal speed of the second particle. So this is the horizontal speed of the hinge, which is, is the linear speed of the hinge times by cosine theta to give you this component along here. And then I add on to that the linear horizontal speed of the mass due to its rotation through this angle theta 2. So then I have to square all of that and add that to the overall vertical speed squared. And that will give me, oh, well, sorry, I think I've said that the wrong way around. Actually, this first one is the vertical speed. The second one is the horizontal speed. But it doesn't make a difference. Okay, the point is this part is fairly easy to get to. Okay, you're just adding up the horizontal speed of the hinge, the second hinge, to the horizontal speed of this mass with respect to the hinge. And then you get its total horizontal speed, and you do the same for the vertical, and you square and add them up, and you get the total linear speed of this second mass with respect to the fixed hinge up here. Okay? And this is the expression. So this expression in the square bracket is the total speed, linear speed squared, of this second mass. Okay? So that's its overall kinetic energy. The kinetic energy of the first mass, and then the kinetic energy of the second mass. So now you just need the potential energy, which is more straightforward to get. So the potential energy, if we take, the height of the hinge as kind of the baseline of our potential energy, then the potential energy of the first mass is going to be minus, because it's below the baseline, minus mgh, where h will be, this height here that you'd find as L1 times cosine theta 1. So that is why we get this as the potential energy for the first mass. Then the potential energy of the second mass is the same thing. It's going to be minus mg times the height that the second mass is under the baseline. So that is the height of this triangle plus the height of this triangle. So that is L1 cosine theta 1 plus L2 cosine theta 2, which is why it appears here. Does it matter where you take 0, or will it give you the same answer in the end? No, it doesn't matter where you take 0. It'll give you exactly the same answer. This is, if you like, this is the most basic example of a gauge invariance. Okay, wherever you choose the height to measure your zero potential from is a gauge freedom. Well, it's a schematic example of a gauge freedom. It's a total choice. It won't matter, because what we'll do shortly when we put it into the Euler-Lagrange equations is we'll end up differentiating with respect to the coordinates and differentiating with respect to the velocities. So any constant factor you add on to the position of any particle, the height of any particle anyway, for its potential, will have no effect. Okay? Hello, YMD. Nice little Pepe there. Okay, so remember that the Lagrangian then is defined as the difference between the kinetic and the potential. Okay? So if we put that all together, we get this expression here. This is our Lagrangian, which is a little ugly at the moment. So we should do a little bit of work to it. Okay? So the work we're going to do to it really just involves expanding out both of these brackets, because generally when you see something that has got a sign and has sines and cosines in a bracket, and if the whole thing is squared, you usually hope that things will either come together such that you have a sine squared plus a cosine squared, which goes away, or such that things will just subtract and cancel each other anyway. Okay. So I expand this out, and I notice that when I expand out, when I get this term here squared and this term here squared, the sine and the cosine will go away, so I'll end up overall with a 1/2 m2 L2 squared theta 2 dot squared. And the same thing will happen with these two terms. And then lastly, something will happen when I combine this term times this term plus this term times this term. That will give me, using another trig identity, a cosine θ1 minus θ2 term. So things will cancel nicely, and you can take my word for it, or you can try it yourself, that when you do cancel things down, you get something a little nicer that looks like this. So this comes from these sine squared plus cosine squared identities, and this comes from, well, the cosine θ1 minus θ2 identity. It is slowly coming together, indeed. Okay. So this is our Lagrangian, and now the technology we have, the mathematical technology we have, is really given by this Euler-Lagrange equation. Okay, we can take this Lagrangian that we've derived, you know, through thinking about kinetic energy, potential energy, and by putting it into the Euler-Lagrange equations, we'll get our equations of motion. Now, this doesn't really bring us anything at this stage more interesting than just using F equals ma would do. You could, if you like, you could have approached the double pendulum problem just as well by thinking about torques and angular accelerations and stuff like that, moments of inertia, but it would have been really ugly and not very pleasant to do. And you would have got to the same result in the end, but actually using the Lagrangian and using the Euler-Lagrange equations circumvents all of that ugliness, and it just gives us the equations of motion that describe the system sort of for free. Well, you know, not for free because we've had to do some work, but it's a lot easier than just using F equals ma and doing things via dynamics. So this is the Euler-Lagrange equation, where here I've used Q as a kind of placeholder for any one of the coordinates in our system. And remember, our system has two coordinates. It's got θ1 and θ2, these two parameters that describe its spatial position. So we'll have two equations of motion from the Euler-Lagrange equations. We'll get one from putting in Q is θ1, and we'll get a second one from putting in Q is θ2. Okay? So here as well, it's important to note that these are partial derivatives. So when we differentiate the Lagrangian, we're taking explicit derivatives of them. We don't care about implicit dependencies, only explicit dependencies. In other words, if you see a term which has no Q in it, no, you know, say for example, we're thinking about Q is equal to θ1. Using Euler-Lagrange basically cuts out half of the degrees of freedom by automatically incorporating constraint equations. Does it? Does it? Surely I mean, it doesn't. It sort of contains within it conservation of energy. If your Lagrangian is not time dependent, then you can show that a certain quantity related to it, the Hamiltonian, is conserved. But I don't know if it automatically includes the constraints, does it? You have to sort of put those in as like Lagrange multipliers. If there are constraints, you know, like say your system is confined to the surface of a sphere or something, I think you have to include those constraints. It's a lot more convenient for doing computations than using Newton's equations. But as far as I know, the Euler-Lagrange equations give you essentially the exact same thing Newton's. With just Newton seconds, you'd have to justify why the bobs don't move perpendicular to the rods. Well, that's true, I suppose so. But I mean, you wouldn't. I mean, that's fine. You just wouldn't include the radius as a variable. You would just set the radius L as a constant. I don't know. I don't see that it would be too much extra work in that sense. If you were, I mean, if you were doing something like you had, oh, I don't know, no, I can't think of an example, but I see what you mean. But I mean, you can do things with like rigid rods and stuff in Newton's laws quite straightforwardly as well. You just set, you know, the length of the rod or something, the position of the bob to be a constant radially. But yeah, I suppose I see what you mean. Yeah. But anyway, so importantly, these partial derivatives are explicit derivatives. So for example, if you're thinking about Q is equal to θ1, when you take the derivative of L with respect to θ1, this term here would totally vanish because it doesn't depend explicitly on theta 1. You might say, well, what if theta 2 dot depends on theta 1? But the point is, in these equations, it's only explicit dependencies which matter in the equation, okay? So now we've got to get to these two equations of motion that describe theta 1 and theta 2. So we first get the first Euler-Lagrange equation by putting in q is theta 1. So now we're differentiating on the left-hand side, we're differentiating the whole Lagrangian with respect to theta 1. And when you do that, the only terms that have a theta 1 dependence are this term and this term. In this system, you're so used to incorporating the constraints by choosing polar coordinates that you don't even notice it, lol. If you had a bead on a sinusoidal wire, it would be much harder to constrain to say on the wire with only Newton second. Yeah, no, that's very true. That's very true. I suppose, yeah, certainly for more complicated systems, the example I was trying to think about was like a particle moving in a bowl. But actually, if it's a spherical bowl, that is also very straightforward. If you like, your example is quite good. If you had a bead on a sinusoidal wire, then yeah, then that is it's much easier to do it in that way. But for this system, I think Newton's laws wouldn't be too impossible. It would just be not as convenient. But I think not as convenient in the same way that any system really is not so convenient as it is with the Euler-Lagrange equations. But yeah, no, that's a good point. Thank you. So yeah, when we differentiate with respect to theta 1, we get this expression here. All of our cosines become sines, and we pick up some extra terms outside from, for example, this one. Well, actually, we don't pick up extra terms, sorry. You pick up a minus sign from the cosine going to a sine, but that's really it. Then we have to differentiate with respect to... Oh, thank you for subscribing, Zwei. That's very kind of you. Very nice. So then we have to differentiate the Lagrangian with respect to theta 1 dot. So this term here depends on theta 1 dot. This term here depends on theta 1 dot. So these are the only ones which will give a contribution from that. What is the face for? I don't understand the face. Anyway. And then we have to differentiate this term that is the derivative with respect to theta dot, all with respect to t. So this is where it gets a little uglier, because now, this term here is fine. This just goes to a theta 1 double dot, but then this term here has got a product of two theta functions, which will depend on time. And in fact, the cosine itself also has two theta functions in it. So differentiating this with respect to time is a little slightly more gnarly, but it's still not too bad. It's still fine, okay? So that's what we get there. And then remember, the Euler-Lagrange equation tells us that the derivative with respect to the coordinate is equal to the time derivative of the derivative with respect to the speeds, with respect to the q dots, or the theta dots in this case. So we put all that together, and it gives us this equation of motion here. Okay, so this is our overall first equation of motion from just thinking about the theta 1 Euler-Lagrange equation. And I've kind of scribbled out here some bits that you can see cancel. So you can see that this term here will be a minus m2 L1 L2 theta dot 1 theta dot 2 times sine blah blah. And on the opposite side, we also have another minus m2 L1 L2 blah 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 blah. The point is these bits will cancel. So our equation simplifies a little more, which is always nice. So this is our first equation in full. And this is as good as it gets. Doesn't get any nicer looking than that, unfortunately. But this is okay, I think. You've got what? 1, 2, 3, 4 terms. That's not so bad. We'll redefine some variables later. Or we won't redefine them. We'll give them new names to avoid having to write them down. So we'll smarten things up a little bit more. But at the moment, this is pretty good. This is not a bad equation. Then we have the second Euler-Lagrange equation to get to derive. So we put this in. First, we look for the derivative of the Lagrangian with respect to theta 2. And if we go back up to where the Lagrangian is, the terms that depend on θ2 are the same terms, actually no, not quite the same terms, are these two here that depend explicitly on θ2. So this one will be straightforward to differentiate. This one will also be straightforward to differentiate. We just have to be careful of that -1 inside here, which will come out the front. But when we do that, it's straightforward enough. We end up with this term here and this term here. Not too bad. Then for the right-hand side of the Euler-Lagrange equation, we have to differentiate L with respect to θ dot. Okay? So if we do that, we get these terms here. And then we just have to differentiate that whole bit up here with respect to time. So again, this is a little bit hairy because you've got 3 theta's in this first term. So we're going to pull up a few more terms, but it's not too bad. This first one, when we differentiate with respect to time, I should have said earlier, but I assume it's clearer also, that I'm using dots to mean d by dt. If you didn't realize that, I can see how you would be quite lost at this point, but a dot just means d by dt. Okay, so θ2 dot is the first derivative of θ2 with respect to time. Okay. So when we do that, this first term, simple enough, goes to this. Then the second term, again, from the product rule, we've got a product of two functions that we're differentiating. This first bit here goes to θ double dot 1 here. Then that's just multiplied by this. And then we have to differentiate this part, which first will bring down a θ1 dot, and then we'll also bring down a minus θ2 dot from here. So we get these three terms. And then we equate this side to this side, as instructed by the Euler-Lagrange equation. And we get this uncancelled expression here. But again, you'll notice this term here, so this is a minus here and a minus here, so overall this term is plus. We have a plus m2 L1 L2 θ1 dot θ2 dot sine blah 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 is equal to the same thing on the right. So I cancel these terms. And then when I do that cancellation, I get this much more compact expression here, which looks very similar to the first expression. So here are the two equations side by side, our two Euler-Lagrange equations. And then in the next line, all I've done is I've divided the first one through by m1 plus m2 L1 squared. Yeah, it's not really much more compact, is it? I mean, it has like one fewer term. That counts. And then the second equation I've divided through by m2 L2 squared. And you'll notice actually that all of the m2's drop out of this equation. There's no m2 dependence. So these are our nice two fully cancelled Euler-Lagrange equations. You wonder how much ink the humble dot has saved over the last 300 years. Probably very many. Very many ink. Yeah, I think, is the dots and dashes, is that, I can't remember whose notation is whose, Newton and Leibniz. I think Newton's one, Newton used the dots and dashes, didn't he? But he also used some other strange notation that is less standard, whereas Leibniz used the d by dx one. Newton's is dots, right, I thought so. So, I mean, you use both of them, really. I think in general, I like the look of Leibniz's one more. I like the d by d something. I think that just looks quite pretty. But then for compactness, you definitely want to be using dots and dashes. At this stage, anyway, I mean, it'd be horribly ugly if I had to write everything as d theta 1 by dt, and then you've got squares and stuff. It will be very... You forgot whose name is on the subscript notation. I don't know what you mean by this subscript notation. What, the one where... Oh, like for partial derivatives, where you've got... Well, you can... There's the GR kind of notation, where if you want to write the derivative of x with respect to, like, the partial derivative of x with respect to, I don't know, y or something, you could write, like, comma y. And then, you know, if you're taking a covariant derivative, it's more like, it's like colon, and then the thing you're taking it with respect to, like the index you're taking it with respect to. I quite like that notation in GR, actually. Yeah, I know the one you mean, where it's like if you've got a function fx, f of x and y, then you'd have the derivative, the second derivative with respect to y would be that, the derivative with respect to x, and then the derivative of y would be f1, 2, and so on. Yeah, I'm not so keen on that notation, but luckily I don't have to work with PDEs enough that it's too much of a bother. Oh, I see. In PDEs you wouldn't even use the comma. Derivative is assumed. Right, yeah, I see. Okay, so these are our two equations of motion. This is what, we've got to try and solve. And I mean, certainly it should be clear right away that we can't solve these by hand. We can't do this, as an analytic solution. I mean, you can't even really do a single pendulum without a small angle approximation analytically. So it's not too surprising that a pendulum tied to another pendulum will also be a little bit tricky. So how do we approach it? So we know we can't do it analytically, not even small angle. No, I don't think so. I think even small angle for this one you couldn't solve analytically. I think it still would have pretty very non-linear and chaotic behavior. So when we solve it numerically, we're not going to use small angle. But no, small angle this would not be solvable. If you think, each one of these signs would just turn into a θ1 minus a θ2. So you've already got a product of θ1 times derivative of θ2 squared, and you'll have similar things down here, and it'll all be quite, very coupled and difficult to deal with. So I should also say, actually, these two equations, these are two second-order nonlinear differential equations, and they're coupled. So we have a pair of coupled second-order nonlinear differential equations, which is difficult to deal with. Well, actually, it's not just the squared term. I think. Oh, actually, yeah. No, sorry. I was thinking, well, this term here would give you something, but actually, this would just be 1. So your second derivatives will be fine. Yeah, I think this is the term that probably mucks it up most significantly. And of course, this term wouldn't be present if you had it just a single pendulum not coupled to another pendulum. So that's really what damages it, I think. But yeah, so we have this system, these two, this pair of coupled second-order nonlinear differential equations. So we have to start thinking we can't solve these analytically, so we should start thinking about how we can solve them numerically. So the way to do that, generally numerical methods for second-order differential equations, there aren't really very good ones. I think the better methods are you can take your second-order differential equation and you can reduce it to a number of coupled first-order differential equations. Okay, I think it's always better to deal with a large number of first-order differential equations than it is to deal with, a single high-order differential equation. So rather than having one third-order differential equation, you would want to rearrange this, define some new variables, such that you would have 3 first-order differential equations. Then these are much more straightforward to solve. The order makes things much harder than the number of coupled equations. It doesn't really matter how many coupled equations you've got computationally, but whereas the order of the differential equation you have makes things significantly harder. So our aim is to turn these 2 coupled second-order differential equations into 4 linear, well, not linear, 4 first-order coupled differential equations. Okay. So the way we do that, we define new variables such that we get rid of the second derivatives in our differential equation. So we want to get rid of these θ1 and θ2 double dots. So the way to do that is to define 2 new variables, y1 and y2, where y1 is I choose to define as θ1 dot, and y2 I choose to define as θ2 dot. And now you can see that, if I do this substitution, if I replace θ1 dot with y1, this θ1 double dot will just become a y1 dot. So it gets rid of the second derivatives in the equation, and then it just gives me 2 new very straightforward differential equations, which is just to say that my first derivative of θ1 is equal to this function y that I don't yet know. But the function y will be specified in part in this differential equation. Okay, so we now have a system of 4 coupled first order differential equations, which is much more friendly for us to solve than these 2 second order ones, which will be quite difficult. I mean, might not even be possible. I don't know. I've never looked into methods that solve first order things without reducing them to, that solve second order things without reducing them to a couple of first order ones. So I'm not even sure if people do algorithms with this. I'm not a very good numerical person. So I've no idea. But as far as I know, this is the way to go. Okay. You're beyond your understanding here, but is WKB the technique that is used to approximating the solutions? No, not in this case. We're not using WKB. The numerical technique I'm going to use is called the Runge Kutta method, specifically the RK4 method, which just means the 4th order Runge Kutta method. So it's very similar to the method we used, for those of you that watched, when we were talking about white dwarf stars. This is called Euler's method, where you turn your continuous x interval or t interval, if it's something that's a differential equation that involves time derivatives, you change your continuous time axis into a discretized grid of little time steps, and then what you do is you rewrite your derivatives as differences between the value of the function on those finitely spaced grid points. So you go from a differential equation to like an iterative equation, to something that is purely algebraic. Now you could do this for this system here, but I think because it is quite a chaotic system, and actually we'll also do some analysis to see how good our numerics are, because what we'll do is we'll solve this equation. Oh yeah, the leapfrog is another method. I think this is even better than the leapfrog method too. Runge Kutta uses like sub-intervals within your time steps to calculate things, as we'll see shortly. So I think it's even better than the leapfrog one. But we'll be able to test how good our numerics are. So once we've solved these equations and we've come up with numerical solutions for the motion of the double pendula, we can then check to see what the energy is at each time step, because of course this is a system that we've not included any dissipative term into. There's no friction here. So the energy, the total energy, kinetic plus potential, should always be conserved. So a good sort of sanity check to see how good our numerics are is to compute the total energy, the kinetic plus the potential, at each different time step and see if it really is constant. Now, it won't be constant, it turns out, because, we're not solving things analytically. So the system, there are rounding errors in the computer. There are, all sorts of things going on that mean the computer is not really getting, the computer knows nothing about conservation of energy. We've not put it in by hand. So the computer is just calculating what is the speed, what is the position to find the potential energy at every time, and then trying to see if it's a constant. But it turns out it won't be a constant because our numerics aren't perfect. So we will see a deviation from conservation of energy, which is fine. It's something we'd expect, and actually it's quite small for the values I looked at earlier. The deviation is not very large. So our numerics are fairly good, but they get progressively worse over time, as you might imagine, where, because the solution to the particular position your pendulum is at, the particular speed it's at, depends on a larger number of times and speeds that have come before. So the longer you go on, the more these errors kind of compound, and you get worse and worse results the further on you get. But for fairly short times, and we can decide later what exactly we mean by short by looking at how much the energy conservation is broken, the numerics are pretty good, and we get some nice pictures too. We'll look at sort of how these solutions kind of deviate for very, very slight differences in initial conditions. This is really what defines chaos. When people talk about chaotic behavior, what they mean is extreme sensitivity to initial conditions. And we'll be able to demonstrate this with our solutions. So once we've coded the numerical solver, and we've kind of built a nice way to look at it, built a sort of nice simulation that will show us the pendulums moving and show us the paths that the second pendulum, which is the most interesting one, will trace out. We'll be able to see how these paths deviate for a very, very small difference in initial conditions, which is quite fascinating, and you produce some really pretty plots, actually. So we'll get on with that. But before we do that, we've got to rewrite these equations as these 4 first-order equations. So the way we're doing that is with this variable transformation here, where we define 2 new variables, y1 and y2, that are equal to theta1 dot and theta 2 dot. Okay. So these are 2 of our new coupled equations, and these 2 are the other 2, where now we replace every theta1 dot with y1 and every theta2 dot with y2. Okay. So here we go. Actually, I've written them here. Here are the other 2 coupled equations. Okay. So these are the simplest ones. Maybe they should be actually the other way around. Might be nicer. So we've got all the time derivatives on one side. All the time derivatives are on this side, and this is equal to some other functions over here. Okay. So my goal now is to rewrite everything so that on one side, on the left side of the equation, I've got something that only includes time derivatives, and then on the right side, I'll have something that doesn't include time derivatives. Okay? Because then what I can do is I can apply this algorithm, this Runge Kutta algorithm, whereby time evolving the right-hand side, I get a new value for the thing on the left, which describes the positions, theta1, theta2, y1 and y2. And then I'll iterate over this. So I'll find all of these different values at all of these different time steps. Sorry, maybe my screen was blocking the dot. It should be clear now that it's just theta1 dot. Sorry, that was my bad. Yeah, my mistake. Okay, so this is my goal, is to have time derivatives on one side and other things that don't involve time derivatives on the other side. Okay, so we've got a 4-dimensional system, as in we've got now 4 parameters, like theoretical phys was asking earlier actually, how many degrees of freedom do we have? We've got 4. We've got 2 position degrees of freedom and 2 velocity degrees of freedom. So my goal now is to have time derivatives one side, other functions on the other side. So to achieve that, I use sort of matrix notation. So I arrange my 4 variables, my 4 degrees of freedom, into a column vector, and then I can take the derivative of the entire column vector. Well, a derivative of a column vector, by that I just mean the time derivative of this, and the time derivative of this, and the time derivative of this, and of this, etc. Okay? So now I'm trying to write my equations in a kind of vectorial matrixy form. Okay? So I have the how did I do this again? So I move everything that isn't a time derivative. So that's terms like this and terms like this. I move these over to the right-hand side. So again, as part of my goal, trying to keep all the time derivatives on one side. So I move all of them over to the right-hand side, and then my other time derivative terms I write in this way. So if you like, this first row here that includes this vector and then all of this, this is the equation here. Okay. these components I've highlighted should contain this top equation. Okay. Oh, sorry. I've highlighted the wrong one. Should contain this equation. I mean, the second equation, as in this one here, is described by the second row. So that is, well, let me let it delete this second row here. Okay. Third row. Wait, what? No. This one is definitely the second row. Yeah. It's okay. I mean, I got it wrong the first time. It's very, very easy to do. Okay. So, what I've done is I've kind of separated out this term here that depends on y2. So it's a 4x4 matrix. Well, at the moment it's just a 4x1 vector. But what will happen is we will end up rearranging it so that we can just have a single time derivative like this on the left side, and then on the right side everything else. We will end up writing it as a 4D matrix times a vector, and then we'll invert that 4D matrix. But don't be scared, because it's a very easy matrix to invert, and I'm just going to write it down anyway, so we won't spend ages doing that. Okay. But you should maybe be able to see how I've managed to write this row here, this equation here, sorry, as this row like this. So everything I've highlighted sort of with these square boxes describes this top equation in the circle. Okay, it's a little fiddly doing these things, but it works out, I promise. Okay, and likewise this top row with the theta and the 0, and then the 0 and the y1 here describes this top equation. Then this third row, which has just a theta 2 here, a 0 here, a 0 here, and a y2 here, describes this equation theta 2 dot equals y2. And then the bottom row, which has a y2 here, 0 here, then there's a time derivative of y1 from here, and this all equals this right-hand side here, you can see describes this equation. Okay, so this is all okay so far. This is what we've got. This is just rewriting our four equations, our four scalar equations, as one vector equation. Okay. But now, remember, my goal is to have time derivatives on the left side, everything else on the right side. At the moment I've got that, so I do only have time derivatives on this side, but this is still not the most effective way I can do it. I can actually rewrite it so that all I have on the left side is this, with none of this stuff, and then I have some different vector on the right side. But I just have to find what that vector is, how we get it. So what I want to do is I want to rewrite this whole left side with these time derivatives as some 4x4 matrix multiplied by this column vector here. Okay, so you can see that, you know, in this first row, in the second row, sorry, for example, the components of y1 and y2 are getting mixed up a bit. They're sort of jumbled. Okay, and the same thing here for this fourth row. I'm also bringing a y1 in here, which is the second component of this matrix. But this is fine. I can rewrite this whole thing as a 4D matrix times this vector. Okay, and what I've done is I've renamed this whole gubbins here A, and I've renamed all of this stuff here B. So if you stare at it for a little while, if you kind of do this matrix multiplication in your head, you should be able to kind of convince yourself that writing this left-hand side in this way, with this particular 4x4 matrix, multiplying by the time derivative of this column vector, gives you all of this stuff here. Okay, so you can see that, for example, let's consider the second row. Now this second row, if I've renamed all of this stuff A, the second row should just be time derivative of y1 plus a times time derivative of y2. Okay, well, let's test it. Let's look at the second row. If you multiply the second row of the matrix by this column vector, sure enough, you have 0 times theta 1. That's correct. There should be no theta 1. 1 times y1. Again, that's correct. This is our d by y1 up here. Then we should have 0 times theta 2. That's correct. There's no theta 2. And then we should have a times y2, which corresponds to this term here. And that is all equal to this second, this left-hand side, sorry, right-hand side here. So this works, and all of these terms in this matrix work, okay, where a and b I've defined in this way, in terms of these functions of theta 1 and theta 2. So a and b are not constants, they are functions of theta 1 and theta 2, okay? So, if I want to rearrange this all so that I just have the time derivative of this single vector on the left-hand side, I have to invert this matrix that I've called capital A. And I like to double underline matrices because, you know, usually they show them in bold, but I like to do that because it's easier to draw. So now I need to invert this matrix A. And again, you can trust me that when you invert this matrix, this is what you get. This is actually not too bad to do in your head, because what you're allowed to do is to invert matrices, you're allowed to switch certain rows. So if I swap this row and this row, and then I swap this row and, sorry, this row and this row, these are columns, sorry, not rows, I misspoke, then you'll see that this is actually just the identity matrix with an A and a B here and everything else 0. So it's like a 2D matrix inside of a 4D matrix. So it's just really just as easy as inverting a 2D matrix. Okay. You take issue with tensor underlining, but you take more issue with the alternatives. Okay. Well, I'm glad I didn't offend. I'm glad I didn't maximally offend you. Anyway, that would have been worse. Okay. So this is what this inverse looks like. You've seen people using bidirectional arrows to... Oh, no, I hate that. I hate that. What, something like... Yeah, that is... No, that's disgusting. Yeah, I don't like that notation either. I completely agree. Not good. I don't even like, you know, for vectors. I don't like that for vectors. Like, for the electric field vector. I really don't like that. I will always go for underlining. Or like, at worst, that with a little tiddle underneath, but not arrows. Have you heard of Runge Kutta method? Is it easier than modified Euler? Oh yeah, so that's what we're using at the moment, the Runge Kutta method. Well, we haven't got to the numerical stage yet, but that's what we're going to use. Exactly. Okay. So I invert this matrix, I multiply on the left by this inverse A minus. Arrows are for beginners, I totally agree. So now I get this time derivative of this 4D column vector on the left. And I've got all this rather, I mean, my handwriting is quite bad anyway, but this is all really small because it was all messy and there wasn't much space, so I apologize if you can't read it very well. But anyway, I get all this matrix gubbins on the right-hand side, which we can calculate just fine. You know, it's kind of ugly, but it's fine. And if you do this matrix multiplication of this 4D matrix, 4x4 matrix, times this 4x1 matrix, you get all of this. So you get another 4x1 matrix with these 4 elements. Okay. So this is the effective form we would like our equations to be in, where now we can start thinking about them numerically. Okay, to try to solve these things numerically. And so as I just mentioned, the approach I'm going to use is the Runge Kutta method. Okay. No, it's fine. I actually said it earlier. You must have just been away when I mentioned it that we were going to use this. So there's no spoiler at all, don't worry. Okay. So I'm going to write it in a particular way. I'm going to define this vector here of our 4 degrees of freedom in this way as theta1, y1, theta2, y2. Now remember, y1 is theta1 dot. So when we come to interpreting this and thinking about what it means, this component here will mean, the angular speed of the first particle. Okay. And then I define another vector that I call f, and this whole thing, f, is just all this nonsense above up here, which I'm not going to write down again. Okay. So in this notation with x and f, I can rewrite this problem in this very neat vector form. Okay. Which looks pretty, amenable to most solving techniques. It looks a lot nicer than what we have written above. But of course, this function f on the right-hand side is rather complicated and is non-linear. So we do have to be careful. You don't just want to go straight in and try the most brute force numerical technique. But for me personally, anyway, I'm not especially interested in numerics as a personal preference. So I'm applying this numerical method without too much diligence. I'm applying it really just because I thought, well, this problem is sufficiently bad that an Euler method might not be good enough. But it's not sufficiently bad that I think I should need to learn any more numerical methods beyond the ones I already know. So I picked the most effective numerical method I know, of which I don't know very many. So many other numerical techniques that would be far better, I'm sure, exist, but that is for someone else to do. Okay, so initial conditions, these are really important, and in fact they'll be really particularly important for us because the whole point of this double pendulum is that its motion is chaotic, meaning it's extremely sensitive to variations in the initial conditions. So if we change these initial conditions even by a very tiny amount, the motion of the pendulum, the pendula, will look vastly different. And we'll do that. We'll compare the different paths that these pendula take when you just perturb the initial conditions by a very tiny amount, which is quite interesting and produces some nice patterns. So I have some initial conditions that in my code I'll leave such that we can fill them in later, okay, so that we can vary these things. Are we also going to show the time graph? What do you mean the time graph? So what I'm going to do is, the thing I'm going to code is a nice little, it's a little simulation that shows actually what the pendula look like, when they're kind of swinging along. And then there's another one that just shows the path traced out in space by the second pendulum bob, the one that is on the very end. That's what I'll code it to do. Okay. So the next step now in this Runge Kutta is to discretize our time intervals, just like we did with the Euler method for looking at white dwarfs. So I'm going to call the time step, the distance between each time grid point when I'm discretizing, I'm going to call h. So I no longer have a continuous time axis, I have points on the grid that are spaced by a distance h apart. Okay, the smaller I make h, the better things will be, because the closer it comes to, a continuous time interval. But obviously also the smaller I make h, the more calculations it'll have to do, and the more difficult, the more computationally challenging it'll be for the machine to do it. So for example, t1, the first time, if we start off at t is 0, which we will be here, then the second time point will be h along from that. The third time point will be h along from the one before that, so 2h, and so on. We just go up by h each time in these discrete time steps we've introduced. Okay. And we define xn as the value of x at one of these time grid points, at the nth one of these time grid points. Okay. So where Tn is calculated, in this way. Xn is just x. Remember, x being this 4D vector of the positions of the pendula and the speeds of the pendula, evaluated at some time Tn. Okay. So, courtesy of Wikipedia, we have this RK4 algorithm here, which is quite nice. You can see actually there's a diagram here, sort of roughly showing how it works. Essentially, it's similar in logic to the Euler method, but rather than just sort of sampling, you know, the gradient on a straight line between the end of the time step here and the beginning of the time step here, you're sort of taking samples in between. So K1 here is, you know, this gradient of the curve x with respect to t sampled at the initial time position, and you know that then takes you along to this point here, and then at this point here you evaluate the gradient again, which gives you K2, and then K2, that'll take you up along to K3, and so on and so forth, and it just gives you a better approximation of what the value of the function is, other than just taking the value of the gradient here, which would be K1, and then multiplying by the time step, which you can see would take you out to here. But instead, you're kind of zooming in, you're dividing up the interval a little bit more to sort of find a better average for this gradient. So K3 is like this averaged gradient between the points you have. Well, sorry, more like... well, K3 is not the average gradient. K3 is one of these terms that appears in the average gradient. The average gradient is this 1/6 times all of these terms here, which give you a good approximation to the gradient between y0 and what is called y1 here, because you're sort of sampling the gradient at a few different points along the curve. Okay, but you're not adding additional time steps. The point is you're doing this intermediately, in between the time steps. So for every time step, you're kind of evaluating the gradient at a few different points. Okay, and finding this clever average that has this 1/6 K1 plus 2K2 plus 2K3 plus K4. Okay, but anyway, we can treat this, if we like, just as a recipe. It's a standard numerical recipe that I am going to use, and we're going to try and code it to solve these equations we've got. So to solve these rather difficult equations here. No, here, where, you know, this f underline is given by this rather complicated vector we had on the right here, and x underlined is this vector of the degrees of freedom. Okay, so that's what we want to do. That's what we want to solve. So let's try and do that. Well, I think the way I'm planning to do this is to write a function which will solve these coupled differential equations for some inputted initial conditions, including masses of the particles, lengths of the particles' arms, lengths of the rods, I mean, some total time we want to run the system for, how many seconds we want to watch it go, and how sharply we want to divide the time interval. So what the length of these little time steps I called h are. So those are what our inputs should be. All of our initial conditions, the masses of the system, and so on. And I want to write this in a function that I'm going to call dpss, which I guess I can't remember why I wrote that shortly before. What stands for double pendular script, double pendular system script, maybe. Who knows? I don't know. I'll leave it as it is, though. Doesn't matter. Okay, so that is what I want to do. And then from this function, I'll call it at different points in a main script, and I'll use it to produce different plots. Okay. So let's look at the Runge Kutta method. So in order to calculate these different later points xn from initial points xn, I need all of these things here. K1, K2, K3, and K4. Okay, so these are the things I need, which we'll have to program into this function. So first let's think about the variables our function is going to take. Well, as a piece of notational change, because it's going to be quite hard to type theta into the computer, I'm going to call... Ah, there we go, I already wrote it down. That was clever. So I'm going to rename theta1 as x1, not to be confused with x underline 1, which is a vector. I'm going to call x2 theta2, theta2 x2. So now, if you like, my vector xn is given by x1, y1, x2, y2. Okay. So the x's correspond to the angles that the pendula are at, and the y1 corresponds to the angular speeds the pendula have, just as a notational thing. Okay. So this function should depend on x1, it should depend on y1. Well, it should depend on the initial conditions anyway, actually. Let's not put them in that order. The first thing it should depend on, I suppose, most obviously, are the masses of the two particles, m1 and m2. It should depend on the lengths that the particles are hanging from in the pendula. And then it should depend on the initial conditions, which I'm going to give this subscript 0. So this is x1 0 is the initial position of the particle 1, y1 0 is the initial speed of the particle 1, x2 0 is the initial position of particle 2, and y2 0 is the initial speed of the particle 2. Okay. And then we need to think about these time step parameters. So if we want the thing to run for a total of t seconds, capital T seconds, we should have that as an input parameter. And we should also have the time step, how small we want to make the time step, as a parameter too. Okay. So now we need to start applying the algorithm. Well, if we've got a total time capital T, and each time step has small step length h between them, then the total number of grid points we're going to need, I'm going to define as the ceiling function of t over h. The ceiling function just means in the instance that t over h is not an integer, the ceiling function will round upwards such that we have an integer, because you can't have a non-integer number of grid points, okay? Because this is just a number that describes how many points there are. As an important physical parameter, I'm going to write g as 9.81. That is necessary. Then, as a sort of standard practice, because we're going to be producing a sort of long grid of the position of every particle for each of these times, for each of these n grid point times, I want to make room for these variables. So I'm going to make room for the x1 variable, which remember is theta1. I have to do the same thing for y1, which is theta1 dot at all these different time grid points. The same for theta2, or as I've called it, x2. This is just so when I create some sort of loop that will go and iteratively assign a value to each one of these x's and y's at different time grid points, that the system has enough room, to deal with it. So it's made enough space to do it. And I do the same thing with z2. Okay. Right. What's making room? Well, it just means, so I'm defining the amount of space that, the code has to leave open for these variables. No, it's not ranges, x, y, and z. So 0s 1 to n literally just means for each of these things. I can show you what it means in here. So 0s 1 to 5 just means a 1 by 5, or a 5 by 1, I guess, column vector of zeros. So now when I start working on this code and I make a loop that will go and find these x values iteratively, it will overwrite these zeros and replace them with the appropriate values. Okay, so it's just so the computer knows how much space there it has to, allocate, if you like, for these things. Exactly, it's just making room for a table of values. Exactly. Okay. Right. So we also need initial conditions. So our initial conditions appear as variable inputs into our function. But our variable outputs are, well, that's an important thing we haven't specified yet. Our variable outputs are x, x1, y1, x2, y2. This is what our function should spit out. It should spit out, a table of values for what the value of theta1 is at every time, what the value of theta1 dot is at every time, and what the value of theta2 dot. Theta2 is at every time and theta2 dot at every time. So these are our outputs. Now we've got a grid of times from time 0 and capital N grid points all the way up to some later time, final time, capital T. So at t equals 0, we have these initial conditions here. But putting this into the matrixy language that we're writing things, this corresponds to the first element of x1 being whatever we input the initial condition to be, and likewise the first element of y1, which describes the speed of y1 being whatever I input y10 to be. The same for x2. Ooh, that should be a 1 up there. And x2 is x2 0, and y2, the first element of which is y2 0. Okay, so this is defining the first element in this matrix of points for x1, x2, etc., as being whatever I input the initial conditions to be. Okay, now something else I will need. Remember, in defining this matrix that I called F, this rather... Why is my pen not working? Oh, yeah, there we go. This rather long thing up here, I introduced these variables A and B up here. So now I want to program into the code an understanding of what I mean by A and B. So rather than having to write out explicitly what A and B are each time, I want to write down what A and B are as functions, defining them with a function handle. Okay, and in fact, the expressions for A and B, so this expression here is the one for A, this expression here is the one for B, are two of these long things that I wrote down earlier. So this is just to avoid any typing error. This is what function A is. As you can see, it agrees with what is written here. And then function B is this. Okay, these are the functions A and B. Then I have to program in this entire ugly vector F. This thing that I called F in this Runge Kutta, like this. So I have to put in this entire vector, which is incredibly long. So again, I don't want to do this. What I want to do is I want to copy the one I wrote down earlier, which I know is correct, to save me typing it all out. But you can trust me that if you type all this in, everything that is written here, what I've got now in the computer is accurate to that. Okay, it's a column vector with 4 elements, where all of them are given as written on the screen there. Okay. Then, now I want to start thinking about this iteration we're going to do. So, the whole point of writing these things discretely is that we've turned the differential equation into an iterative equation, where the next grid point along, the n+1th grid point, depends only on the value on the nth grid point and these constants here that we calculate according again to information just about what is on the nth grid point. Okay, so all of these things we can work out from information about the nth grid point, but will tell us things about the n+1th grid point. So we're going to have to iterate over things. So I define a for loop that runs from 2 to give me the second grid point up to capital N, which is the final grid point. And now I need to define these K1s, K2s, and K3s as they are given here. So our function f actually doesn't explicitly depend on time. If we go back up and look at it, you'll see that there's actually no time in here explicitly. All we have is y's, x's, x's and y's, x1, x2, y1, y2. So really we can sort of ignore the part in the Runge Kutta formula which talks about, this tn plus h over 2 and so on. All we're interested in is this part here when we plug this in. So I have my function f that is described here. So all I need to do is evaluate the function f, which was this right-hand side, this horrible 4×1 vector, at these particular points. Well, so first I just evaluate it at the point n, which initially will be the grid point 1, which will then help us calculate the grid point 2, which we'll then use to calculate the grid point 3, and so on. Okay. So first I calculate k1. So for that, I just have to take the value of the function f that I've specified at this value of x here, or this value of x, this value of y, and so on. And that is given by this formula. Okay. Function f of the n-1th element in x1. So for example, when n is 2, this first thing this iteration will go through, it will take the first value of x1, because that is x n-1, which is x1, 1, the first element of x1, the first element of y1, the first element of x2, the first element of y2, and then it will calculate this value k1 as we have described here. Okay, then next we have to calculate k2, which now depends on xn, but also on k1. So now we'll have to plug in the k1 we've just found here, will appear in our expression for k2. So now we're taking f of evaluated at xn plus 1/2 h k1. So that is given by this rather long function, which again I will just write down. That is what happens when you plug it in exactly as is written here. And then we have the same for k3, where now k3 has some dependence on the value of k2. Nicely in order. Yep. It does all look quite well laid out. And then again, k4 will be some function that depends on k3. So we've got it like this. And there we go. That's what we have. So these are the k's we need to calculate. And then there is this last part here, which just tells you actually how you calculate the n+1th value of this vector x from the nth value, the value of x on the nth grid point. So now we just have to put that in. Okay. Did I write that down? I didn't write that down, but that's okay. This one is not so bad to write out. So that gives us x1 n, the nth value of x1, is equal to the n-1th value of x1. I'm now just programming in this equation here, okay? Given we've already found these values k1, k2, k3, and k4, okay? So for x1, this is x1 n minus 1 plus 1/6 times h times... Then inside of here, we've got, well, remember, k1 is... Actually, k1 is not a vector here, is it? No, it is. K1, K2, K3, and K4 are all 4x1 vectors. Okay? Because, you know, F is a 4x1 vector, a 4D column vector, and it's equal to F evaluated at some particular values of x1, x2, y1, and y2. So these are 4D vectors. So for x1, which is formed, if you think, you know, this vector equation contains within it component equations. So the first component equation, now it's a little confusing because I've used x to mean the vector that contains, remember, x1, y1, x2, y2. And I've also used x as this variable here that means θ1 and θ2. So this is a pretty bad choice on my part. But anyway, if we think about the first component of this, what the first component of this is saying is it's saying what I've called here x1, the nth value of x1 is equal to, sorry, the n plus 1th value of x1 is equal to the nth value of x1 plus 1/6 times h, and then you've got the first vector element of k1 plus 2 times the plus the first element of k2 plus the first element of k3 plus the first element of k4. Okay, because this k is a vector. So, you know, this vector equation is like the first component of this is equal to the first component of this plus a half h times first component, first component, first component, first component. And likewise, say the fourth component of this, which corresponds to y2, will be equal to the fourth component of this vector plus the fourth component of this vector plus the fourth of this, the fourth of this, the fourth of this. Okay? So inside of here, I need k11 plus 2, k21 plus 2, k31 plus k41. Okay, that's what I need. And then it's the same thing for y1, x2, and the others, except now I've copied and pasted it to save some time, but I've now got to fix it. So now y1n is going to be y1n minus 1, plus now it's going to involve the second component of k1, the second component of k2, the second component of k3, and the second component of k4. Then this one here will be x2. x2 will involve the component x2. It will involve then the third component of k1, the third component of k2, third of k3, third of k4, and then y2 will involve y2 evaluated at an earlier grid point, plus the fourth component of k, fourth component. Okay? Right. So that is how the function evaluates those things. And that is actually it done. Yeah. Well, it's not quite it done. Now we have to specify the output argument. So remember, these are our output arguments we called x1, y1, y2, x2, y2, and so on. So now I have to specify what these output arguments are. So I should be outputting x1, y1, x2, y2. This is what our function should be throwing up out of it. So what are these defined as? Well, these are all of the things that we just calculated above. This whole for loop here is creating an array for every single time step for this x1 variable, y1, x2, and y2. Then the final thing this function spits out should be that total array that has now been constructed at every one of these grid points. So it should be the function x1 all the way along all of its n values. Oh, well, I can just write it like that, actually. If not, it'll pick out the nth value. The colon just means all values it will spit out. Y1, likewise, will look like that. Y2 will be that. And you stop pressing enter. Sorry, X2 will be like that. I misspoke. And Y2 will be that. Okay. Why don't we need this within the for loop? Well, because these are the final constructed arguments. So if you like, what it's doing here is for every n in the for loop, it's saying the nth element of x1, which remember we made room for up here. We defined a 1 by capital N array of numbers. Then what the for loop is saying, for example, follow the logic for n equals 2. It's saying when n equals 2, it calculates these k1s by taking the function f of the first value of x1. And remember the first value of x1, first value of y1, x2, and y2, we defined explicitly as input variables of our function for our initial conditions. So it calculates all of these k3, k4, etc. and so on. Yes, exactly. It's filling up as it loops. Exactly, absolutely. So for n is 2, just completing this, for n is 2, it will now say the second element of x1 is equal to the first element of x1, plus then, you know, these k1s it just calculated, these and the k2s and stuff, and all the way in this standard formula for the RK4 method. Okay. And then, yeah, then it will move on to n equals 3, and then it will fill up the third element of x1, third element of y1, third of x2, third of y2, and so on. So yeah, it will fill up all of them, and then what we're doing at the end is we're saying the output variable that we defined in the first line of the function. So the first line of the function, I said the output is, you know, these four outputs, x1, y1, x2, y2 here. Now I need to define what those final outputs are. So I define them as this fully constructed n element long vector for all the x1s, all the y1s, all the x2s, and all the y2s. Okay, so that should be okay. That should work now. Right, but we'll only know if it works once we've tested it. So let's test it. The first thing I want to do is just to produce a plot that shows the motion against time. Not anything fancy, not a fancy simulation or anything, just a pure graph of what it looks like. So let's think about what initial conditions we should use. I'm going to choose mass of 1 kilogram, M1, the other mass of 2 kilograms. Both lengths I'm going to give as 1 meter. I mean, the thing is, even without going too crazy, you can make this thing look pretty chaotic. So we don't have to make anything too crazy. Then I'm going to use the solver function on this. What else do I need? Well, I also need, I need initial conditions. So I need my initial positions of this thing. So I can call my x1 initial position, I'm going to give as pi over 2. So the initial rod, if you remember what this thing looked like all the way right back at the start. Remember, theta 1 is now called x1, Theta 2 is now called x2, and y1 is the initial speed of the first particle, so the initial angular speed of the first one, and y2 is the angular speed of the second one. Okay, the total theta 2 dot. So the initial conditions I'm giving, initially I'm having this first pendulum horizontally, and I'm going to give it an initial push. Let's give the first pendulum, the first bob, an initial angular speed of pi radians per second. So, you know, it'll take 2 seconds, at this initial speed, it would take 2 seconds for it to go all the way around a full circle. So we're giving it quite a big push. Then x2 naught, let's call that pi over 3. So this is initially at 60 degrees to the vertical, the second theta 2 here. And I don't think I'm going to give it a speed. Initially, the second one is just standing still. Okay, those are our conditions. Right, now let's call the function. So remember, our output variables are x1, y1, x2, y2. And we're calling the function we've defined, which took initially m1, m2, l1, L2. I haven't defined the time steps. So let's go for capital T. Let's go for a 30-second long run of this thing, and let's set the time step to 0.01 seconds. So the time is divided up into grid points separated by 0.1 seconds. Okay, so we've got L1, L2. Then let me just check the function. So the arguments, the next arguments were the initial conditions, then T, then H. So initial condition, that's x1 0, y1 0, x2 0, y2 0, capital T, then H, as we've defined there. So let's see, will this work? Okay, it didn't crash, but I also forgot to actually tell it to plot anything. So let's get it to plot. Let's get it to plot both curves. So let's get it to plot x1, and let's get it to plot x2. Okay. Ah, right. Okay. Can you see that? More or less. There you go. So that's what we'd sort of expect. It looks like pretty, you know, interesting motion. It starts off kind of sinusoidal, but then it certainly goes a little bit weird as this pendulum is moving. But this isn't very good for actually visualizing what's going on. So now we're convinced that the code at least is not totally stupid. It works somewhat anyway. Now what I'd like to do... Hang on, why does that go up to... Why does it go up to 15? It shouldn't go up to 15, should it? How is it over 2 pi? Does it flip over? What do you mean, how is it over 2 pi? Oh, as in, well, you know, but what I mean is, surely the maximum it should be is 2 above 0. Because, you know, this thing is, if you look at it, L1 is 1, L2 is 1. So surely the biggest it should be 2. I don't know how it's getting an x2 that is larger than 2. Oh, I'm an idiot. Oh, thank you. Yeah. Yeah, exactly. Thank you, Harel. Yeah, exactly. Yeah, no, very good point. Yeah, as Harel says, we're plotting theta here. Oh, so that's what you meant, it flips over. Oh, exactly. Yeah, it flips over. My brain totally went then. Exactly. So yeah, this thing, when it flips over, it won't modulo 2 pi. We could, if we like, you could just put in modulo 2 pi here. Actually, why don't we do that? What is the MATLAB function for modulo? Is it just mod? We can add that in quite easily. Mod AM returns the divisor A by N. So if I just put in mod of it and then 2 pi, that should fix it. But this is actually not the most interesting plot anyway. So if I want to plot this mod 2 times pi, then I do the same thing down here, mod this 2 times pi. Okay, that's not what I expected it to do. Why has it done that? Is it just cutting? You know what? It doesn't matter. This is not the most interesting plot. What we'll do is we'll make it so that you can actually see what the pendula look like. It is angular position with respect to time. Well, specifically, it's respect to the number of grid points, which is related to the time just by multiplying by little h, the time step. Okay, but anyway, the most interesting part is where we'll show what the pendulum actually looks like. I define 0 as hanging straight down, haven't you? Yes, I have. Yeah. Yeah. Okay, it's fine. Harlem Snipes, I know that the prank is getting old. It's not particularly funny. But anyway, hello. Okay. So, let's code the thing so we can actually see what it looks like. That is what I'm interested in doing. So, what I want to do okay. We'll open up a new figure window. Now the idea is I need to just draw a line. Basically, I just need to draw a line segment between the position of the hinge here and this bob here, and then draw a second line segment between this hinge here and this bob here. And then I just need to sort of redraw the line segment, kind of time evolve the position, and refresh the plot every time, and it'll just show what the pendulum looks like. Okay, so I need to first convert from these angular variables I've got, where I'm describing it in terms of θ1 and θ2, to describe it in terms of the x positions and the y positions of the first mass and the second mass. Okay, so that's what I want to do. So I need to do another loop, because the point is I want to update the position of this line segment at every single time step. So at every time step, it will update the line segment to show the position of the two pendula, of the double pendulum. Okay. So again, I have to have a for loop from 2 up to capital N, where capital N, well actually I haven't defined capital N yet. I've defined it inside the function, but it's not a global variable, so I need to define it here. Capital N is, as I defined in the function, it's the number of grid points. So it's the ceiling of the total time and the length of my time steps. Okay. So also, I want to hold on, because I don't want the function to plot right away. The hold on just means basically that the figure window is still able to update when you change the thing you're trying to plot. So I put it on hold so that it doesn't yet finish plotting in the window. Then I need to calculate the x positions and the y positions of these masses. So x pos 1 is the x position of the first particle, and that is going to be given by, well, let's look at it. The x position of the first particle that is going to be L1 times by sine of θ1. But remember, θ1 I've called x1. And also, actually, I should label these with an index n because I'm trying to fill out another matrix for the nth position in this matrix. So that is x1, the x position of the first particle, then the y position of the first particle at the nth time interval will be given by L1 times cosine of θ1 at that particular time interval. Then we've got the x position of... Oh, hold on again. It just means... So if you... What I'll do in a minute is I will have some function in here that will be like plot blah blah blah. And if I didn't put the hold on, what it would do is it would plot, and then it would, as soon as it goes back to n1, it would overwrite the plot it had before. No, sorry. So what I'm going to do actually, is I'm going to have two plot functions in here. I'm going to have one which tells me to plot the first rod of the pendulum, and a second plot that tells me to plot the second rod of the pendulum. And what the hold on does is it means these two plots won't overwrite one another. Because if they did, what would happen is the computer would quickly plot the first rod. So it would plot this. Then it would see the second plot, and it would get rid of this plot and plot the second one. But I want them to both be on the screen simultaneously. So I put hold on just to say to MATLAB, until I tell you, hold off at the very end, don't finish plotting. Keep taking my instructions on what to plot on this figure. Okay, that's what it means. So now I need to find the x position of the second particle. So the x position of this particle. So again, like we said earlier, that is going to be the length of this triangle plus the length of this triangle. So that is, well, I can write it slightly, it's going to be the x position of the first particle of the hinge, the x position here, plus this extra length here. So that plus L2 sine x2, or θ2. Okay. Then we've got the y position of the second particle, which will be likewise the y position... well actually, you know what, these should be negative y positions. Okay, the position of the first particle, the y position, minus again this extra length that comes from here, this length here. So that is L2 times times cosine x2 n, like that. Okay, those are the positions. Now, what I want to do is to draw a straight line. Thought you'd be doing the more chaotic movable double pendulum. What do you mean movable double pendulum? I mean, sorry, both of these hinges here are movable. Both of these masses will move. This is the standard double pendulum that goes. Oh well, I mean, this top hinge doesn't move, if that's what you mean. This isn't on some rod that can move around. That would be interesting though, to do it so that this was maybe you could tie this to a spring or something. That would be quite interesting on either side. But I haven't done that. This orange one is totally fixed. But these ones are free to move on these rigid rods. Okay, so what I want to do is I want to draw a line segment for the first rod and another line segment for the second rod, which updates at every time interval. So the way to do this, I had to look this up actually. I hadn't done this before, plotting line segments, is to take your notation is kind of like this. You've got these two square brackets, and then what you do is you put in the coordinate, the first coordinate, where you want to start drawing the rod from. For here are the first square bracket contains the x coordinates. So this would look like zero. So I'm drawing 0 to the position of the first mass, and then 0 to the position also of the first mass. And actually there's some odd notation you have to put in that somehow tells it to draw a line segment. I'm not sure, I've never seen this notation before, but apparently if you put a dot and colon, it draws line segments between these coordinates. Which is quite odd. I've never had to use that before. But anyway, that's what it does. So this is now, what this draws is, this draws the first line segment of the rod. The first rod like that. Okay. So it draws it between what I've defined here as 0, 0, where, you know, this is 0 here, this is 0 here, and this position here, which is has x coordinate, what I've called x pos underscore 1, and y coordinate, what I've called y pos underscore 1. It draws a line segment between these 2 points. Nice blazer. Oh, thank you very much. Yes, the top hinge drive has amplitude + frequency. No, I should have. That would be an interesting extension. It wouldn't be too hard to do, but we'd have to go back and derive all the Euler-Lagrange equations again, and I don't have the energy to do that. But yeah, that would be very possible. So now I want to do the same thing. Now I want to draw the second line segment. Where now this line segment is going from where the first line segment ended to this end here, which I've defined by x2 pos, y2 pos. So now the end of this line segment is the position of the second particle, and the start of the line segment is the positions of, are the positions of the first particle, like that. That looks fairly correct to me. And then the last thing I want to do, purely for aesthetic purposes, is to plot, put a bob on the end of both of the pendula. So rather than just drawing a straight line, what I'd like to do is I would like to add a bob. So at the end of each pendulum, x pos 1, y pos 1, and I'm going to make this bob red and make it out of a little circle. And I'm going to do the same thing for the other particle, the second mass. And well, if you like, I can make this one blue. This will be a little blue bob on the end. Okay, that all looks all right to me. Then the last thing I need to do is, because at the moment if I run this, this is just going, it's going to, well, actually, let's see what it does, and then I'll explain why I have to correct it afterwards. So let's run it, see if it works. It says busy. Why is it busy? Shouldn't be that busy. Oh. What's it doing? What the? Ooh. Ah, you know what? Okay, I know what it did. So what it's done is it plotted the entire motion and then it showed it to us. But I wanted it to open and plot it as it was going. So, why has it done that? Why has it not plotted it as it goes? Ah, well also, actually, another thing I should have done, this is perhaps not related to why it's not plotted as it goes, but I should have set the x limits and the y limits so that the frame stays fixed. So the x limit, I want to go between minus L1 plus L2 all the way up to L1. Oop. L1 plus L2. And the y limit, I want to go from the same place. Just so it keeps it in a box that is the size of the maximum displacement x and y wise it can have. But why did it not show it all in one go? Maybe, no, you know what, I know. I don't need the hold off. If I have the hold on, then, well, let's see. Let's see what happens. What's it doing? Why isn't it happy? Unbalanced delimiters. Oh, okay. You need square brackets to specify the x and y limits. See, again, it appears to be plotting it all in one go and then just ramming it up. Why is it doing that? I mean, this is going to be the same thing as before, but it should plot it live. Not very good. Let me put a pause in so that it pauses for every time step second, so it doesn't try to plot it all in one go. Oh, is it frozen? Oh, nope, it's unfrozen. Okay. Okay, why is it flashing? That looks kind of dodgy. Okay. What has gone wrong here? Oh, why is it back? Go away. Oh, it's still running. Okay, it's stopped now. So... Wait, what is x1 defined as? x1 is all of these points. Okay, that's fine. Something has gone wrong here. Is the hold off before or after the end? Well, I've taken the hold off out. I don't think it should actually make a difference. It should just open the window, then start doing the plotting. Well, actually, also this should be a 1, but I don't suspect that will make any difference. Oh. Oh, no. I forgot to close the window before. Maybe that's the reason why. Okay, let's try... Okay, stop. Okay, that's not there. Let's try it now. Whoa, why is it coming up immediately like that? That's so bizarre. Okay, I killed it. Try again. Okay, something has gone deeply wrong. What is it doing that's wrong? Okay, that is fine. That is fine. Yep. Yup. Uh-huh. Uh-huh. Ah. I know what it's doing. I don't need these. Right. Okay, fingers crossed. Okay, there we go. Right, so yeah, this is doing something, but it's not quite what I want it to do. So this is the point. What it's doing now is it's plotting it, but it's not refreshing the image, as in it's not clearing the step before last. So I can, although this looks pretty cool, we can fix it and make it even better. So let's cancel it. If it will let me cancel. what I want to do is at the end of every single run, I want to clear all of the previous stuff on the plot using this function. Okay, so now, oh, it's not even stopped yet. Go away. Oh, you go away too. What are you doing? Oh, it's still not stopped. It still says pausing. Uh-oh. Come on, MATLAB, don't die. It probably really didn't like plotting all 3,000 of those lines in very quick succession. It appears to have frozen slightly. It's still struggling to pause. Okay, well, worst comes to worst, I can just close it. You know what, I'm going to do that. I'll just close it and reopen it. It doesn't make a difference. Stop and end now. I saved it anyway, so there is no difficulty. End now. Kill it. Kill it dead. Okay, there we go. Right, so well, I should run this section first to make sure everything is as it should be. Okay, it still produces those plots we saw before. Then now let's run this one. Ah, there we go. That's what we've got. That's what we were hoping for. That is the plot we wanted of the pendulum, which is pretty cool. It shows what it's doing. You can see there's where it flips over. Very nice. It's quite hypnotic, actually. I quite like just staring at it, to be honest. But it actually worked. That was good. Finally. Yeah, it is quite nice. And, you know, we can do all sorts to it. We can change parameters. We can give it a bigger push. We can make one of the masses much, much heavier. See what happens. All sorts of things. Well, let's do some of those things. What do we want to change? Does anyone have a preference? What should we change? We can make one mass much heavier than the other. Whatever. What does anyone want to do? Give me a parameter for M2 and give me an initial speed for Y2 and a mass for M2. Okay, bottom mass heavier. What number? What number should we go M2? What do you think? Like 100? Go nuts. Let me know, what do you think? What mass for M2? Okay, M2 is 10. M1 is 1. Big mass. Let's start with 10 and then we'll see. What about, we could give it a push. We could give the second pendulum a larger push. That's what Y2 corresponds to. Can you change gravity? We could do. I don't know how interesting it would be, but I mean, you know, we could change what we've called G in here, and that would change gravity. I don't want to do that right now. We can try that later, but I think by playing with the masses, we'll get some cool stuff without it. So I'm gonna give it a big push. I'm gonna give it a big push of 10 pi. Okay, 5 pi. Let's go 5 pi. 5 pi. So let's first just generate all of the numbers with the solver. Oh, has it done it? Well, yes, I need to cancel that. Ooh. Okay, something interesting has gone on there. Now, what does this do? Whoa, okay, yeah. So the second much heavier mass, we've given a much bigger push. So it is basically just spinning the whole thing around. That kind of makes sense. I mean, this motion actually appears very regular. I guess this is you know, close enough to an ordinary pendulum such that one of the large masses is so much bigger than the other mass. It basically just acts like an ordinary single pendulum. So that's sort of expected. What if we make, I think what would be interesting is if we make the first mass M1 very, very big and the other mass very, very small, but give it a very big push to see that it goes, you know, I think it'll go kind of crazy. So let's do that. So let's swap these masses around. Let's go 10 for M1, 1 for M2, and let's make L2, well, let's make L1 like 3 times longer. And let's give let's give it an even bigger push, the second mass. Oh, okay, interesting. So it looks like this is just going to decouple and we're just going to get two totally sort of separate circular motions going round. That's interesting, yeah. So the second smaller mass has got a really, really big push. So it's just spinning right the way around the whole time. And the bigger one has also got a big push. And because it's very, very massive, it's not really affected by the motion of the smaller one spinning around. So I think it's quite interesting, actually. The smaller one is basically just acting to sort of slow down the speed, kind of create a slight oscillation in the speed of the bigger one. It does look a lot like planets, actually. Exactly. It's like, yeah, you've got the sun in the middle, then you've got like the Earth going around the moon at the end. That's interesting. Okay. Well, that was fun. So let's set things back to where they were before with masses and lengths. Let's get rid of this speed here. So now everything is basically exactly as it was before. Now, what I'd like to do now is I'd like to plot the trajectory of the second mass. So not just showing what the pendulum looks like, I now want to try and get a sketch of the path that the second one is tracing out. Because I think that'll be quite interesting. Okay. And then we'll really be able to compare when we vary these initial conditions. We can vary the initial conditions for two different ones and look at what the path is doing. Okay. So now we're looking to trace out the ends of the pendulum. So, right. To do this, I am going to... What am I going to do? Well, actually, this is... Now I think about it, this is actually exactly the same as the code we've already got. So I don't need to put the M back. All I need to do is I need to stop it clearing after each time, change the figure name, and then what I'm going to do, well, I'm going to get rid of these end bobs. I'm going to get rid of the position of the first bob, because actually the position of the first bob is not very interesting. But I'm going to look at the position of the second bob, and I'm just going to specify that it is traced out as red points, red dots. Ah, there we go. So this is the position of the second one. This is still with the kind of crazy motion, though. We're not looking for the crazy motion at the moment. But that was interesting. That looked sort of elliptical there, which was fun. Oh, come on. Why won't it end? Once these things get started, they really don't want to end. It's because it's updating so many times. It's not taking... Okay, let me pause it. Sometimes when you click quit debugging, it ends it. Okay, there we go. It ended it. Right, so let's generate it for our first lot of initial conditions we had, with the masses as equal. Oh, actually, the masses weren't equal, were they? One of the masses was heavier. Which one was it? No, initially we had that. M2 was actually 2, not 1. Okay, so now the second mass is twice the size of the first mass. So now... Ooh. It didn't like that. Unrecognized function n. Oh, well that's because I didn't... Okay, yeah. Sorry. That's fine, that's just a minor thing. Ah, there we go. Oh, why is it plotting two things? Oh, so now now it's plotting both. It's plotting the position. So this one here, the one that is darting around more, is the position of the second mass, M2, and the upper one that is just staying confined to this roughly circular thing is the position of the second mass. So you can see actually where the numerics are slightly going wrong, in that this thing in reality should be totally circular, but of course it's not. Actually, that's something interesting to do that I said we would do. Let's look. Let's try to look at energy conservation. Because what energy conservation will tell us... You know, I don't need these things, actually. That should work just on its own. Let me try that just quickly. Okay, yeah, that's fine. Axis square after plot. Wait, what? What does that mean? I didn't get what you mean, Atom Fighter. Okay, let me get rid of this. Okay, so now it's just plotting the motion of the second bob, which is the most interesting one. Oh, this one is actually very interesting, what it's doing. Huh. That is pretty cool. I want to know what this looks like with the actual pendula, not just the... It's an axis ratio of the plot that makes the aspect you look wrong. Oh, I see. Ah, I didn't know that. Okay, I'll do that. Thank you. If I can actually get this thing to end. There we go. So axis square. Axis square. That's not how you spell square. Okay, let's see. Whoa. It didn't like axis square. Aspect ratio is the unit space. Maybe... Am I typing this function in right? Actually, sometimes they do like capitals, don't they? Oh, I see, like that. Oh, right, okay. Oops. Oh, after the plot, not right. I see, okay. Let's try that. Ah. That does look more square. Okay, nice, cool. Thank you. That's great, I'll have to remember that. Cool. So yeah, now I want to look now at what this thing actually looked like. No single quotes. Is it... Oh, did that not do it? Oh. Maybe I imagined it looked squarer. Ah, okay, now it definitely is another shape. Huh, I see. Oh, right, thank you. Okay, cool. Yeah, I want to look at what this thing looks like. Oop, go away. In the actual pendulum-y plot. Go on, quit debugging. It's being a bit cheeky again. I don't know why it won't quit debugging. Okay, wait a minute. I'll just cancel it. Kill it. Smother it to death. I'll just relaunch it. But yeah, that plot looked pretty cool. I want to see what it looks like with the actual animation of the pendula. Oh, H is the time step from the solver. So it just means it's plotting it in real, seconds. So every time step in real time it's plotting, it's updating the image. So it looks a little nicer. Well, so it plots it in real time. Okay, so first let's do the solver. Then this should be with the same initial conditions. So now when I run it with a little animation, okay, there we go. Yeah, that does look like it did before. Ooh. Ah. Ooh. Hypnotic. You are feeling very sleepy. Very sleepy. Oh well. Okay. Well, anyway, so yeah, now we've got it so that we can see the traces that is made by the second bob, what it's doing as it goes along. Okay. Which is pretty nice. So now what we'd like to do is we'd like to look at two different sets of initial conditions, and put these initial conditions, very near to each other, and see how the thing changes. Oh yeah, put axis square for the stickball one too. That's a good idea. Yes, thank you. Okay, axis square, and well, I suppose if I just put it on the last one, it should. Well, maybe I put it on the first one. In fact, let's see. There we go. Or maybe I should just put it before the figure. I'm not sure exactly how it does it, but yeah, that's good. Nice. Sweet. Thank you for the tip. That does look a lot more representative. Awesome. I like it. It's quite pretty. Okay, so now I want to just basically redo this plot, but for two different sets of initial conditions. Okay. So I am going to take what I've got up here. This is my function up here. And let's just put everything in. What I'm going to do is I'm going to find two lots of solutions. So let's do it for the same time step, the same time duration, 30 seconds. And now, though, what I'm going to have is I'm going to have M1 with set 1 of initial conditions. Oh, no problem. Thank you. Thank you for clicking the Discordy thingy. So the _1 here, _1 now indicates that, well, actually, you know what? Let's leave them the same mass and same length. These should be our control variables. But now the _1 on the initial conditions is just indicating this is the first set of initial conditions. But what we're going to do is we're going to do two different sets of initial conditions that are, potentially similar, but also might be different. So now I'm labeling these lower ones with a subscript 2 to show this is for the second set of initial conditions. And now we should just choose what these things are. So if we take, as we did before, mass 1 was 1 kilogram, mass 2 was 2 kilograms, L1 was 1, L2 was 1 as well. And then we should specify the initial initial positions and initial velocities. So x1 initial position, that is the initial theta angle for our first set of initial conditions we're thinking about. Let's set that equal to what we had before in the plot we already produced, where we also had the initial speed was set to, what was it? Was it set to pi? I think it was pi. It's here. Yep. So it was pi, then pi over 3, then 0. Okay. So that was pi. The initial position of the second mass for this first set of initial conditions was pi over 3. And the initial speed for that second mass, was 0. We set it as. Okay. So that is our first lot of initial conditions. This is one first initial configuration for this system. We've put it in. So now I want to do the same, but for a different set of initial conditions. So let's start off very small. Let's make the difference between these things just something as simple as I'm going to adjust the position of the second mass by pi over 100. So very, very tiny. DPSS, it's not that I can't even remember what I meant it to stand for. I think it was double pendulum solver script or something, except it's not a script, it's a function. I just quickly before the stream, I was like, oh, I should probably name these things before I start. So I just put DPSS, because I think when I was trying to run this through myself, where I was testing it before the stream, I used DPS for the original solver I wrote, so I couldn't use DPS again. So the second S, you know, stands for whatever you like. The S stands for S, like the J in Homer J. Simpson stands for J. The S in DPSS stands for S. Or one of them does, anyway. Okay, so these initial conditions of these two systems are the same, except for the position, the initial position of the second mass is perturbed distinctly from the other one by pi over 100. So a very tiny amount. Well, not a very tiny amount. We can make it even smaller. We can say pi over 1,000. And now I want to compare how this will look. Well, so first I need to... the S is silent, exactly. First I need to write the solver down properly. So this first line here is solving for the first set of initial conditions. This second line here is solving for the second set of initial conditions. And what I'm going to do then is I'm just going to steal my code from up here. And I'm going to plot both of these paths that are traced out on top of one another. Okay. The S is for savant. Okay. So, well now let's rename some of these things. Let's just add an extra one here for... These are really ugly variable names, but it doesn't really matter. A 1 here for all of the positions of the first set of particles. First set of initial conditions, that is. And the same thing down here to show these correspond to the first lot of initial conditions. And now I just need the exact same thing. But now I'm just going to change all of the last ones to 2s, because this is corresponding to the second set of initial conditions. Okay, because of the position of my arm, I'm trying to work arrow keys with my pinky, which is not very accurate. Okay, right, that all looks good. Now, what I want to do is I want to plot x1 pos1 1, x1 pos2 1. Yes. Yeah. Ah. That should be a 2, which means that should be a 2 up there. What I was plotting here was the x-coordinate of the first particle and the y-coordinate of the second particle. So actually, the thing we plotted up here was not a physical thing. Oh, I should have cancelled that. It was a weird combination looking at the x-coordinate of one particle and the y-coordinate of the other particle. Okay, that's a slight error. That's fine. But now that should be corrected. So now this is truly the x and y coordinates of the second end of the mass. Oh, and it's not even showing for you. There you go. If you post this code in Discord, then I will clean, refactor, optimize, and repost it on the Discord. Oh, sure. I mean, if you feel like doing that, you know, go ahead. That would be very, very useful for me to see that, and I'm sure helpful to anyone else that wants to play with some of this. So yeah, absolutely, I will do that, definitely. If I forget, do just remind me, but I'll try to remember. Okay, so this is what this is the thing we just plotted before, but corrected from what I was accidentally plotting was actually the x position of the first particle here, and the y position of the second particle. But now it is definitely plotting the x and y positions just of the second particle. Okay. Right. So now I'm trying to plot the path that is traced out by the first particle, the second particle with some initial conditions, and also the second particle with some different initial conditions. So these are now 2's to show that this is taking the second set of initial conditions, and hopefully this will run. Okay, so at the well, actually, you know what? Let me get rid of it, because you know what? I've plotted both of them in red. I should plot them in different colors. No! Stop! No spoilers. Okay. I want to plot this one in blue. The second set of initial conditions is in blue. So these systems are totally the same masses, same lengths and everything. The only difference between them is that the second particle in one of them has a little perturbation to its angle of pi divided by 1,000 on top of the initial condition for the position of the second particle for this set of initial conditions. Okay, so it's a very tiny difference. But let's see how that tiny difference manifests over time. Okay, so at the moment they look red and blue right on top of each other, starting slightly to separate. And oh, there we go. Yeah, totally other directions. So it took a little while, but you can see this tiny sensitivity to the initial conditions, and now these things have gone in wildly different directions. Their motion now, you would have no way of knowing that they started off so close together based on how they're moving now. So it looks totally different. Make it BO instead of B. Sure, I can make the dots larger. I can, as in just make the B larger and keep the red the same, or make them both O. What do you mean? There. Okay, let's do that. Oh, go away. I forgot to cancel the window. Stop. No. Bad. Okay. Right. Cancel the window. There we go. Okay, so now the B1. Oh, I see. That's quite nice, yeah. Yeah, so you can see when the red one is kind of deviating from the center of the blue one. Oh, there we go. Off they go. Very nice. So this is an example, of chaotic behavior. How these things have such sensitivity to their initial conditions that even when they're within, a thousandth, well, what would it be? Like a tenth of a, well, no, what would it be? Like 100th of a degree of each other initially starting out. The trajectories they form afterwards are wildly different from one another. And this is what people mean by chaos, this extreme sensitivity to initial conditions. And, we could play with this for hours. We could change, we could give one of them a slightly larger push than the other and have them starting at the same angle. We could change all sorts of things. But you can see that, it's really very sensitive to these tiny changes in the initial conditions. The bath of a butterfly wing in Brazil causes a hurricane in the USA. Yeah, it's that kind of thing. That's often what they call things that describe chaos. They describe it as this butterfly effect. That, if you go back in time, you kill a butterfly and it affects the entire history of the human race in some way. Which is not really true, but, chaos is really a very sort of mathematical thing. This extreme sensitivity to initial conditions. I mean, certainly weather systems are an example of very difficult non-linear differential equations. Yeah, I was just thinking that's another Simpsons episode where Homer has to keep going back in time and like crushing different animals to see how it changes to give him back the future that he was used to, that he lived in. But yeah, weather systems are an example of very strongly coupled, very non-linear differential equations where, like Atom Fighter was sort of alluding to, slight deviations, in pressures and stuff in one part of the world, I mean, not literally as strict as something like a butterfly wing in Brazil causing a hurricane in the USA, you could probably prove that those perturbations would actually die out rather than would grow. It depends whether perturbations grow or die out in these systems. But certain perturbations of certain sizes will grow and will have enormous effects on the system. Now, I mean, I don't know much about. I'm not a climate or an atmospheric or a weather person. But these are interesting systems, and this is sort of a simple example of how this chaotic behavior works. But I think I'm going to cancel it now because it's probably going to start getting a little bit grumpy if it runs for too long. So the last thing I want to do, that I kind of alluded to earlier, was a sort of sanity check to see how good this numerical approximation is. Oh, well, damping would be interesting, yeah. Damping would tend to, to reduce the system to rest. So it would actually stop it being so chaotic, because eventually the system would lose all energy and would just disappear. It wouldn't keep going. Ah, this thing is frozen again. Hang on a tick. But yeah, what I want to do now... Why does it keep doing that? I don't know why it keeps doing this. But oh well, it doesn't matter. I can just cancel it because it's all saved anyway. But what I want to do now is I want to do a sanity check for how the numerics of this problem are doing and how physical... There we go. How physical this thing is. Exactly. I want to check energy conservation. Because of course, like I said earlier, we've not plugged energy conservation into this thing. So it doesn't know about energy conservation. So it would be interesting to see whether it automatically is respecting it or whether it is slightly violating it. And actually, it will turn out that it is slightly violating energy conservation. This system is not perfect because, you have rounding errors, you've got all sorts of different computational errors and numerical errors that are compounding and causing this system, not to behave in a strictly sort of analytic, physical way that it should do. So it will deviate away from a perfect solution because it isn't a perfect solution, fundamentally. What integration scheme are we using? We're using an RK4 scheme. This is one we coded, we wrote a little function to do it here, and then we've just been playing with some plots and showing how the initial conditions deviate away from it. But now what I want to do is I want to kind of do a sanity check. So I want to evaluate the total energy of this system and see whether it's conserved. It turns out it won't be conserved. So in order to do this, I basically have to take these expressions we found earlier for total kinetic energy, total potential energy, but now instead of subtracting them as we did when we were calculating the Lagrangian, we instead want to add them to give us the total energy. And this is one of the things I really should have typed up earlier to save the time again, but it doesn't matter, it'll only take a couple of minutes, because it'll be interesting to see how much this system does or doesn't, but actually does, violate energy conservation. Okay. Ooh. So at the moment I'm entering in this first term for the kinetic energy of the first particle, and let's call it, well, let's just write it as x1. Sorry, it's not x1, is it? If it's y, if it's theta1 dot, then it's going to be what we've called y1 squared. Then we also have then the kinetic energy of the second particle, which is slightly more awkward to write down. Then we've got this entire bracket, and then inside of this entire bracket we've got two whole brackets squared. So in the first whole bracket we've got this L1 times theta1 dot, which is given by y1 theta1 dot, times cosine of θ1, which is cosine of x1, and that is plus L2 times θ2 dot, which is y2, times cosine of θ2, which is x2. Then the second bracket in the kinetic energy of the second particle, we have L1 times θ1 dot, which is L1 y1, times sine of θ1, which is sine of x1, plus L2 θ2 dot, which is y2 times sine of θ2, which is sine of x2. Okay, so that's all of the kinetic energy terms, correctly, I believe. Then we've got the potential energy terms, which we're adding on. So these are negatives, so that means we've got minus, well, I just realized actually you can't see everything I've written there. So let me, there we go. Now I've just shared it over a different line. I'll do minus dot 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 again. So this is minus, and then this dot 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 just means I'm skipping to another line. So now I'm taking off minus m1 times g times L1 times cosine of θ1, which is x1, minus m2 times g times, then the thing inside the bracket is L1 cosine θ1, which I call x1, plus L2 times cosine θ2, which is just x2. Okay, that all looks sensible. Now, I can't remember when I last defined g, so let me... Actually, I defined it above. I think, actually, now I think about it, what I will have to do is do this for these initial conditions. This first system we did, which was just the one system, not the two systems, where we were comparing how they evolve with different initial conditions. This is just the one system on its own, where I get these outputs, x1, x2, and y2, the one that looks like this. So this system, this is what I'm now plotting. I'm plotting the total energy of this system. Oh, it just froze for a minute. Fair enough. Yeah, it's a little bit jiggedy now, but oh well. I'm going to plot the total energy of this, and we'll see how good our approximation is, whether it respects conservation of energy, or whether the numerics are, you know, a little bit janky and kind of get it slightly wrong. Okay. So here we go. This should calculate the total energy, and then let's plot the total energy at each time step and see what we come out with. Ooh, there's an error. Where is the error? It doesn't, it says line 30. Well, I've got Y. Where's there a Y? G. Ah, does it know what G is? Ah! Thank you, thank you. I see, I thought I started writing down what G was, but then I thought for some reason I defined it earlier on. Yeah. Thank you. Oh, I see. Oh, I didn't even read that first line. Thank you. Yeah, very good. Huh. Wait. That's not right. That's not what it should look like. Yeah, that's not what that plot should look like. Hmm. L1 squared is wrong. Ah, oh well, that is definitely something, yep. And I wrote L1 times 2. Hmm. Oh, that fixed it. That was all that was wrong. Oh, interesting. Okay. Right. Well, yeah, so this is the initial total energy, which we agree on. You know, you could calculate this by hand if you like, just from the initial conditions that this particle is starting off. The first one at pi over 2, the second one at okay, the second one at pi over 3. The first one has initial speed of pi radians per second, and this one has no initial speed. So you could calculate the initial total energy of this system. But what you can see is that over time, it's kind of, it appears to be losing energy. The numerics are going slightly wrong, such that the energy in total is decreasing, but it's not too bad. It decreases by 0.04 joules over 30 seconds. So for 30 seconds of the motion, you know, but certainly for the first 7.5 seconds or something, it's pretty good. It doesn't really lose much energy at all. There's not much numerical mucking about. What does the spike represent? I was just wondering that actually. It seems to be it plateaus and then it spikes, which is quite interesting. Why would it do that? Hmm. Phase slip. What do you mean a phase slip? As in like an error from it not like doing it mod 2 pi an angle, or why would it have those spikes? Computation jump from Atan 2 kind of stuff. I have no idea what Atan 2 is, to be honest. I'm not a numerics person. Um, yeah, don't know. I'm not sure what those spikes are doing. That would be interesting, though, to think about. But yeah, but you can see there anyway, for a relatively, you know, an okay amount of time, uh, this thing seems to be conserving energy, the system overall, you know, which is a good thing. I suspect that we could improve this if we decrease the step size. That might be something interesting to see actually. Let's try and do that. Let's increase the step size. Sorry, decrease the step size by a factor of 10. So now our time steps are. Would it be interesting to compare it to something like Leapfrog? Well, so someone mentioned Leapfrog. To my understanding, RK4 is always better than Leapfrog, isn't it? As far as I know, RK4 is better because it takes sort of okay. Leapfrog is symplectic, but only second order, you believe? Hmm. I'm not sure. I'm not sure which one would be better in that case. Leapfrog conserves the shadow energy. Right. I don't know what that means. I said at the start I'm not a numerics person, and I stand by that. um, it would be interesting to compare. Certainly, if you want to have a go on it, please do. I think like Atom Fighter asked, I'll put the code in my Discord after somehow, and then anyone can have a play with it if they want to. So it does sound quite sinister. What was it? Shadow energy. Shadow energy. Yeah, it does sound quite sinister. Let's see what happens anyway when I decrease the time step by a factor of 10. So now the total energy. Ooh. Well, that's interesting. Well, I mean, so it stays flatter, of course, because the scale here is much smaller. But these spikes, the spikes have become comparatively larger than the overall decrease in the energy, which is quite interesting. So the spikes get worse. So you know the largest amount by which the system seems to be violating conservation of energy gets worse when you add more time steps, but overall the average total energy is more constant. Is there a way of understanding that, why the spikes would get larger for smaller time steps? Surely when what goes to zero? When the time step goes to zero? Well, I mean... You can also see those spikes. Do you also see those spikes for a simple pendulum? Well, let's see. So, in theory, if I set mass m2 to 0, this thing should just give me simple harmonic motion, assuming there's no nasty place where it's dividing by anything. So something... Well, what if I also set L2 equal to 0? Then... Okay, it doesn't like that. Well, if L1 was 1, it seemed to be giving simple harmonic motion for the first particle, but I don't know what's happening to the second particle. So this here, I should say, is like angular position. Well, let's see what this looks like. Let's just view what it actually looks like. Well, that's weird. Oh, well, actually, no, it's not weird. It makes complete sense. Now the second particle is just going to keep spinning, I guess. It's got no mass. Yeah, no, I don't think this is a good thing, putting it. I don't think it's a good thing setting one of the masses equal to 0. Because it's now like... Actually, it's definitely not a good thing, because in one of the equations we had, in this equation here, this second thing we got from the Euler-Lagrange equation, for the second equation, we later divided this whole equation by m2. So we certainly can't set m2 equal to 0. That's not a good thing to do. But we could probably set... Oh, you bugger, stop it. We could probably set m1 equal to 0. Or you say you could set it... Oh, 0 length. Actually, well, oh no, hang on. No, because we also divided by L2. We've also divided by L2 here. And we divided by L1 here. I think the only thing you can sensibly set to 0 is m1. But then what will that do? Will the pendulum know that it's allowed to kink, or will it... What does this look like then? So this is the first mass here being 0. No, you know what? That's not good either, actually. Whoa! What the hell happened there? It just yeeted itself away. Okay, I want to watch that again. Okay, so it seems to be going fairly slowly, all fine. Coming down. And then Yeet! Wow, okay. Yeah, I've no idea what's going on there. You know what? It's maybe just not a good idea to set any of these things to 0. um, fair enough. We could like theoretical phys suggested we could exactly and like atom fight. Oh no, sorry, like atom fighter said, not theoretical phys. We can set one of them very big and one of them very small. So hopefully we'll avoid zeros like that. So let's set. Well, I'll pick the things you picked. So let's pick M2 is 0.0001. Sorry, M1 is 0.001 and M1 is 1,000. Let's go for that. That seems like it should. Ooh. Oh dear. Hang on, why is it not recognizing G? Right, I feel like the same thing is going to happen again. Oh no, is it broken? What has gone on? It did it again. Why is it doing that? What is the chat saying? V approaches C. Yeah. Quantum teleportation, time travel. Yeah. Something quite funky is clearly going on. Okay, let's put everything back to normal, and if it's still broken, then we really are screwed. Okay. This is what everything was before. Okay, it's not totally broken. Right. Now, let's set the first mass very, very tiny. Let's not go very tiny, just pretty tiny. 200, 100th, and 100. Okay, yeah, no, it's still not liking that. The speed is like 0, and then several, a lot times the speed of light. um, at the top of the code, well, it's already clearing it all up here. I think it's fine. All right, let's leave the second mass. Here's M2. See what happens. Again, wow, that's even worse. This is like cosmological constant, order wrong. Crikey. That's very odd. Okay, what about 0.01? Okay, it doesn't mind that. Why? It seems to get grumpy when one of the masses is smaller than the time step. Now, is there a way of understanding that? Don't know. I don't know. Yeah, it must be that it's not stable. I can't understand why it's not stable immediately. I mean, well, okay, well, how about we try that? How about we increase the time step size and put it back down to a small mass and just see what happens? So this is the same mass it went crazy on. Oh, hang on. This is the same mass it went crazy on before, but with a much smaller time step. Okay, yeah. So it was a resolution issue. Yeah. Okay, that's fine. Great. Wait, what was the point of all of this? What were we trying to do? Ah, we were trying to see whether the energy still has that same problem for a single pendulum. So this is what the motion looks like. Why is this so slow? Right, I feel like this pause H is doing something wrong. The pause H is pausing for the period of seconds that the time step is. But you know what? I think maybe because it's such a small time step, when it pauses, really it pauses longer just because, I don't know, for some reason it can't manage pausing for such a short time. Maybe it's going a bit crackers. So let's pause for a shorter time. Oh, no. That was just bad. Oh gosh. Okay, small time steps seem to muck it up in some way. So let's do this. Go away, that. It closed all figures that are open. Bring that up. Yeah, we're looking at the spiky behavior. That's it. Oh, close all. Oh, I see. Not clear all, close all. I must have misread that. Oh, okay. That'll be helpful, yeah. I suppose I should put it at the top of each one of these. Because when I'm running these separate sections at different times. Okay, right. Well, let's okay, that looks reasonable for that motion where one of the masses is much smaller and it looks relatively purely sinusoidal. This is what it looks like. It's still a bit slow. I suppose it's okay, but oh, it sort of jumped then. Oh, yes. Okay, something. Wait, which mass is large again? I forgot which mass is small, which mass is large. Mass 1 is this mass is very tiny. The other mass is about 100 times bigger. 200 times bigger. Don't know why it's jumping. You say phase slippage. What is phase slippage? I don't think I understand what this is actually. Maybe it's too long for you to type and kind of explain. I don't know. I should look it up. What is it? Phase slippage. Jumps in phase angle of your pendulum. What causes it though? Is it just too low resolution? Or I don't know. What was interesting to me is that the spikes seem to get proportionately larger than the overall decrease in energy when you increase the time step. I thought that was quite interesting. I don't know why though. It has to do with the maths of angles. The maths of angles. Ooh. Not sure. Okay. Well, oh no, it's struggling to pause again. Oh, there we go. Well, anyway, let me put this relatively back to normal. Okay, this is what it was before. So I guess the point of that was just to see what would happen to the energy with those spikes. Actually, we didn't even check the energy. Well, let me check it now for that system. So yeah, so okay. So for that system we were just looking at, the energy drops pretty drastically, actually. Yeah, the energy you've got negative 10,000 as your energy, which does not seem very physical to me. So something to do with that is going very wrong. Almost a diagonal. Yeah, so it doesn't like that for some reason. It seems to do okay when you've got relatively similar small masses. Then it looks all right. It's still a bit slow. It wasn't this slow before. I don't know why it's gone so... Well, actually, I did change the time step now I think about it, didn't I? The time step when it's 0.01. This is lower resolution, but for some reason it looks prettier. I think maybe I need to think about this pause H thing, which is kind of mucking up how long it's paused for. But yeah, I think it looks quite nice like this. For simple masses, it does need a little bit more work. I will post it in my Discord if anyone wants to take a look at it. Oh, there's a little bit there where it looked a bit janky. But it gives the idea, and it shows some chaotic behavior, which I thought was quite interesting in plotting these sort of phase plots for different, but not too different initial conditions. Sure, I will put it in, yeah. So let's look at those again because they look quite cool. This is the plot for two particles that start off with an initial difference in the angle between them of only pi over 1,000, so a very small difference. You believe it is to do with the change of radian angles and computations. Okay, fair enough. Yeah, I'm not sure I'd have to... Oh, change in sign. Ah. Oh, something like it... Oh, I see. Like, oh, like maybe when it gets to like when the angle is like, I don't know, 1.9 or something of pi, it rounds to 2 pi, then modulos it so it goes to 0. So it appears to skip round by a big angle, or I don't know. No, but it still wouldn't skip round by that big of an angle though, would it? Because it would. I can see how like there's like kind of like a branch cut between there, isn't there? Between 0 and 2 pi. So maybe there is some way that it skips there and the phase slips, like you were saying. That's true. Yeah, well, so the spiking did reduce. So the spiking reduced, just the total average drop in energy seemed to reduce more. Maybe that's a better way to think about it, where the spiking didn't necessarily get worse, just it wasn't made as better as the total decrease in energy was made better by increasing the step size. Maybe that's a way to... I mean, that's a theorist's way of saying, it doesn't matter. That's my way of doing it, but I'm not sure. Read in particular Atan 2's computation. They discuss it there. It's a physics thing. What is Atan 2? Oh, arctan 2. Oh. Two argument arctangent. Okay, I'll take a look at that. Oh, right. Yeah, I wasn't sure what that function meant. Ah, interesting. Okay. Yeah, I will do that. Well, I guess for now maybe what I'll do is I'll post the code in my Discord. If anyone wants to take a look at it, and if anyone hasn't joined already, you can feel free to. And then yeah, I guess we can talk about it a bit more on there or something, because it is interesting. I do find these things quite cool. But yeah, anyway, that was sort of a ground up kind of look at double pendula. So we started off talking about the Euler-Lagrange equations. We wrote a numerical solver for them, and then we've kind of investigated how the initial conditions affected, which is quite interesting. And we built quite a nice little illustration of how the thing actually physically looks with these two pendula. But now MATLAB is frozen, so it won't let me show that. Oh well, doesn't matter. These MATLAB codes will make you a greater physicist. Yeah, computing and coding is very important. It's something I should invest more time in, really. But this has been interesting anyway. So yeah, there we go. There's, to end on that, there's the little thingy going around. You are in essence running a laboratory experiment in a pseudo world. That's very true. It is pretty cool. I was trying to think if, before I was doing this, if there was a way I could build a little physical double pendulum beforehand, but I think there are far from enough materials at my disposal to do so. So I didn't attempt it. But yeah, anyway, I guess I'll leave it there. So thanks a lot for joining, everyone. And I will... yeah, not physical double pendulum. Actually, yeah, that could have worked. 2 shoes and a shoestring. I was thinking I would have to do it with rods, because, I don't know, this one was with rods, but with a string, actually, that would have been very doable. That's a good point. This is why I'm not an experimentalist. I don't have that ingenuity to think of these things. But no, that's a good point. I should have done that. But yeah, anyway, so thanks for coming, everyone, and I'll see some of you next. Oh Christ, what day is it? Next Tuesday. Tuesday is office hour, where we can chat about some other things and look at some physics memes. Then Mario Kart on Thursday, and should I programming projects more often? I should do. Yeah, that is true. I should do a few more. We did one. It started because we did one when we were looking at white dwarf stars, and we were trying to solve this equation. This like coupled equation of state and hydrostatic equilibrium equation to get the density profile of the star. And for that, you had to use some sort of numerical method, but it was a very primitive numerical method. That was just a normal explicit Euler scheme, I think. Or was it implicit? I think it was explicit, actually. So it was very basic, but it gave a fairly good estimate, and we got a good estimate of the Chandrasekhar mass. But yeah, I'd have to think of if anyone has any suggestions for any interesting numerically things, preferably not things that require too much knowledge of numerical methods, unless they are very willing to hold my hand walking through it. Oh, Monte Carlo stuff. Oh yeah, that could be cool, actually. Yeah, that's a good point. There are some interesting things you can do with Monte Carlo simulations. Do more t equals L minus U. T equals L minus U? What is that? You're kind of biased, but you would love to see it. Brownie in motion. Ah, that would be fun. Yeah, that could be something. Spring and mass. What do you mean? As in, like, the motion of a mass on a spring? The Ising model? Oh no, I can't look at the Ising model. Too many years of being forced to do condensed matter physics has meant I have a natural repulsion to the Ising model. Oh, like more Lagrangian stuff. Oh, I see. Fractal curve streams. Oh, that would be cool. Yeah. Oh, yeah. We should create some like fractals or some, generating things like this. Oh, I'm sorry, Yang Yang. I wish I could love condensed matter physics. Everyone I know that is a whose opinions I really respect as physicists say, "Oh, you're so wrong about condensed matter physics. It's so brilliant, so wonderful, and it has so many fantastic analogs to high energy physics and other things." But I just can't. I just can't. Some systems are interesting in that they're analogs to to things I'm actually interested in. But condensed matter in itself, if you put condensed matter on it, if you give me a physics problem and you don't tell me it's a condensed matter physics problem, it's some, I don't know, like strongly coupled system or something, whatever, then it's probably interesting. But if you tell me it's a condensed matter system, I won't be happy about it. But that's my personal bias. You and Java. Oh, okay. Yeah, I know nothing about Java, but fair enough. You're not a condensed matter guy, but you did your bachelor's thesis on numerical simulation of the Ising model. Oh, okay, interesting. Interesting. MATLAB is Java. Is it? Oh. I have no idea. I'm completely illiterate about these things. I just know MATLAB is very similar sort of qualitatively to Python in use anyway, from what I've seen of it. Well, yeah, anyway, I suppose I'm very good at doing these very long drawn out endings where it just kind of turns into chatting. Type Y in command console. I think we did this. Wait, what? Type Y is in Y in here? Is that what you mean? Oh my god. The bald and not excessively bald and not excessively smart hamster obeyed a terrified and not excessively terrified hamster. What the heck? I've never seen that before. Why? The fool, the tall, good, and smart system. To fool the tall, smart, and good system manager. Why? The rich, and tall, and good system manager suggested it. He wanted it that way. Why? The programmer suggested it. Why? Mara suggested it. Why? To please a very terrified and smart and tall engineer. Why? The tall system manager obeyed some engineer. Why? To satisfy some programmer. Why? Mary Ann wanted it that day. What the hell is this madness? I've never seen this before. What? It's an Easter egg for when you ask yourself why during coding debug. Wow. I did not know that was a thing. It's a matrix that stitches grammar components. Wow, you learn something new every day. Thank you for that. That is very interesting. I had no idea that MATLAB did that. How wonderful. Brilliant. Okay. Well, on that bombshell, let's leave it there, I suppose. Thanks again all for coming, and I'll see some of you on Tuesday, and then maybe some of you on Thursday as well for some Mario Kart. But let's chat in between then, I guess. Come and join my Discord, and we can talk about this numerical thing a bit more. But yeah, thanks all for coming, and see you guys later. Okay, bye. Bye-bye.